The assessment of the universe's commencement and its non-stop extension is presently at a critical stage, with cosmology defying some of its most basic uncertainties. A key focus is determining the rate at which the universe is expanding. For over 10 years, two major approaches to measuring this expansion have produced conflicting results. Recent observations of the current state of the universe indicate that the rate of expansion, known as the Hubble constant, is around 9% higher than predictions derived from data from the early universe. Scientists had hoped that the James Webb Space Telescope, JWST, the most advanced telescope ever created, would provide a definitive resolution to this issue. However, the groundbreaking data from JWST has only widened the discrepancy, raising questions about the validity of the established cosmological model. This has sparked intense debates within the scientific community about whether new physics are needed to revise or completely replace the current theories that have held for more than 40 years. This possibility is both exciting and unsettling, as it suggests we may be missing a fundamental aspect of the universe that could radically reshape our understanding of its origins. The beginnings of the universe trace back to the Big Bang, a titanic explosion that, in an instant, produced energy, matter, and space. From this, the universe began as an intensely hot and dense plasma, a mixture of matter and antimatter particles. These particles collided and annihilated one another, but scientists believe a subtle imbalance allowed slightly more matter than antimatter to form, preventing the universe from destroying itself. Gravity then pulled the plasma together, heating it to the point where sound waves, known as baryon acoustic oscillations, propagated through it at speeds greater than half the speed of light. Meanwhile, the dense energy content of the early universe stretched spacetime itself, pushing matter far enough from the extreme heat to survive. As the universe expanded like an inflating balloon, normal matter is thought to have started clumping around invisible dark matter, eventually forming the first galaxies. These galaxies are believed to be interconnected by a vast cosmic web, linked through dark matter and energy. As the universe continued to expand, both the energy density and the rate of expansion gradually diminished. However, around 5 billion years ago, galaxies began to recede from one another at an accelerated speed, driven by a mysterious force referred to as dark energy. The most widely accepted theory for dark energy is that it acts as a constant force embedded in spacetime itself, woven into the fabric of the universe's expansion. This force, known as lambda in Einstein's theory of general relativity, maintains a constant density as the universe grows, while the density of normal matter decreases over time. Over time, dark energy became the dominant force driving the expansion of the universe. Alongside dark matter and normal matter, these forces form the lambda cold dark matter, lambda CDM model, which describes the universe's evolution and predicts its ultimate fate. Heat death, also known as the Big Freeze. While many of the model's predictions have been confirmed, the nature of dark energy and dark matter remains unresolved. One of the most significant challenges facing cosmology is the Hubble tension. Depending on the method used, measurements of the universe's expansion rate yield conflicting results. This discrepancy is so pronounced that it has become one of the field's most pressing issues. Observations from the early universe suggest a higher rate of expansion than the lambda CDM model predicts. These early measurements have been rigorously tested and validated through various observations. According to Nobel laureate astrophysicist Adam Rees, who led the team responsible for the latest JWST measurements, the only possible explanation for the discrepancy is that our current model is missing something crucial. Measuring the expansion rate of the universe requires more than simple observation. One primary technique involves examining the cosmic microwave background, CMB, which represents the universe's first light, emitted around 380,000 years after the Big Bang. This imprint is visible across the entire sky and has been extensively mapped. Between 2009 and 2013, the European Space Agency's Planck satellite produced a detailed map of the CMB, showing that the universe is nearly uniform. However, slight temperature variations mark areas of higher and lower matter density. These variations reflect the imprint left by baryon acoustic oscillations, helping cosmologists calculate the Hubble constant, yielding an estimate of approximately 67 kilometers per second per megaparsec. Another method involves examining Cepheid variables, pulsating stars whose outer layers expand and contract in a regular pattern as they absorb and release radiation. Discovered by astronomer Henrietta Swan-Leavitt in 1912, this behavior allows astronomers to measure the star's absolute brightness, which can then be used to estimate their distances. The Cepheid variable method, part of the cosmic distance ladder, has been a crucial tool for measuring vast distances across the universe. In 2019, Rees and his team used this method to study the Large Magellanic Cloud. Their results were striking, showing a significantly higher expansion rate of 74 kilometers per second per megaparsec compared to the Planck data. When the James Webb Space Telescope was launched in December 2021, expectations were high that it could resolve or confirm the discrepancy. With its 6.5-meter wide mirror, nearly 3 times the size of Hubble's, and superior infrared capabilities, JWST could observe fainter objects and detect a broader range of wavelengths. Studies comparing Cepheids in the galaxy NGC 4258 to supernovae revealed results nearly identical to Rees's previous findings, with an expansion rate of around 73 kilometers per second per megaparsec. These findings have caused a stir in the cosmological community. Some suggest measurement errors, while others propose the need for new physics or a combination of both. This debate highlights the possibility that dark energy's behavior may have evolved over time, influencing the expansion rate at different stages of the universe's history. Resolving these mysteries will require both advanced observational tools, like JWST, and theoretical frameworks capable of incorporating new data without discarding the successes of current models. The implications of JWST's discoveries extend far beyond cosmology, touching on broader astrophysical questions about the origins of life and the conditions necessary for life on other planets. By studying distant galaxies, astronomers hope to uncover clues about how Earth-like planets could form around other stars, offering insights into the prevalence and diversity of life across the universe. Looking ahead, the James Webb Space Telescope is expected to continue making groundbreaking discoveries, not only in cosmology but also in planetary science, star formation, and the study of exoplanets. By analyzing the atmospheres of exoplanets, JWST aims to identify chemical signatures that could hint at the presence of life or conditions necessary for life to exist. Its ability to observe the most distant galaxies and faintest celestial objects will deepen our understanding of how stars and galaxies formed in the early universe. Moreover, its advanced infrared capabilities will allow astronomers to peer through dust clouds, shedding light on the processes that govern star and planetary formation in our own galaxy and beyond. As scientists grapple with the tension between JWST's findings and established cosmological models, new theories and frameworks are being proposed to explain the discrepancies. These include modifications to the lambda-CDM model, alternative interpretations of dark energy, or entirely new physics that account for phenomena not yet observed. This era of cosmology, fueled by JWST's precision and range, promises to reshape our understanding of the universe and its origins. It is a reminder that scientific inquiry is a continually evolving process, where answers often lead to new and more profound questions. The discoveries made by JWST may not only solve long-standing mysteries but could also open doors to entirely new fields of study, fundamentally altering how we perceive the cosmos and our place within it. In the coming years, collaborations between ground-based observatories, other space telescopes, and JWST will refine these measurements further. Missions like the European Space Agency's Euclid, NASA's Nancy Grace Roman Space Telescope, and the Vera C. Rubin Observatory are set to complement JWST's findings, providing additional data to help resolve the Hubble tension and explore the nature of dark matter and dark energy. The pursuit of answers to these cosmological questions not only deepens our understanding of the universe but also highlights humanity's unyielding curiosity. As we continue to explore the cosmos, we inch closer to unveiling the secrets of existence itself, an endeavor that connects us to the stars and to the mysteries that lie beyond. The future of cosmology is set to be shaped by this growing synergy between theoretical advancements and observational capabilities. As the James Webb Space Telescope, JWST, and forthcoming missions continue to push the boundaries of what we can observe, the need for new and more robust models of the universe becomes ever clearer. One exciting avenue lies in further exploring the nature of dark energy. If dark energy does indeed evolve over time or has properties that differ from the cosmological constant lambda, this could revolutionize our understanding of the forces governing the universe's expansion. Such breakthroughs might also bridge the gap between general relativity and quantum mechanics, two pillars of modern physics that remain fundamentally incompatible at present. Similarly, advancements in our understanding of dark matter, another enigmatic component of the cosmos, could lead to breakthroughs in particle physics. Experiments at facilities like the Large Hadron Collider, alongside next-generation dark matter detectors, may one day provide direct evidence of the particles that constitute dark matter. This, in turn, could shed light on how dark matter interacts with normal matter and influences the large-scale structure of the universe. At the same time, JWST is poised to continue making groundbreaking contributions to exoplanet research. By observing exoplanets in unprecedented detail, JWST could help identify the chemical signatures of atmospheres, such as water vapor, carbon dioxide, methane, or even oxygen, key indicators of habitability. Such observations have the potential to transform the search for extraterrestrial life from speculative to evidence-based. In parallel, the study of galaxy formation and evolution is entering a golden age. JWST's ability to look back over 13 billion years allows scientists to observe the universe in its infancy, uncovering clues about how the first stars, galaxies, and black holes formed. These observations will challenge and refine existing theories, potentially altering our understanding of how complexity arises in the universe. As technology and data collection methods improve, artificial intelligence and machine learning are becoming increasingly vital tools for analyzing the vast amounts of data generated by observatories like JWST. These technologies will enable researchers to identify patterns, detect anomalies, and make connections that might otherwise go unnoticed. The interdisciplinary nature of modern cosmology is also drawing on insights from other scientific fields. For instance, biochemistry and planetary science are helping to inform our understanding of the conditions necessary for life, while advancements in high-energy physics provide clues about the fundamental nature of the universe. As we stand on the cusp of a new era of discovery, the questions raised by the James Webb Space Telescope serve as a powerful reminder that our understanding of the cosmos is far from complete. Each revelation brings us closer to answering the profound questions about our origins, our place in the universe, and the ultimate fate of all things.